Hi, and welcome to this second video in our series on forces, and second video, so it's going to be Newton's second law, as we're working through all his laws. And this one is the biggie. This is the one that gives us the basis for the vast majority of what we're going to be doing on the course. So, here we go. So we're going to be looking at Newton's second law to calculate forces and motion. So in the last video, we just looked at kind of resultant forces and how we can find force and so on, but this time we're going to start linking things together a little bit more. So, here we go. We know from the first law that if an object's going to accelerate, then some resultant force must be acting upon it. And obviously, the more force you apply, the greater acceleration. That's kind of fairly obvious. But what Newton then said was, therefore, the change in motion, i.e. the acceleration, is proportional to the applied force. And he also decreed that it was dependent on the mass of the object, i.e. the larger the mass of the object, the bigger the object, or the heavier the object, the more force you need. Again, fairly common sense stuff. So what that did was gave us that simple equation there. So you've got a constant proportionality. If you remember your GCSE maths, y is proportional to x, was y equals kx. Here we've got force is proportional to mass times acceleration, and you've got that constant value there. So what we need to do now is just figure out what's that value of c, and this is where some very, very careful choice of how we define a unit makes the calculation a whole lot easier, and this was the genius of Newton. He said that the force required to give an object of mass 1 kilogram and acceleration of 1 meters per second squared is what the Newton is. So if we have a look at what that's going to do to our equation, so if we put a force of 1 Newton in here, a mass of 1 kilogram, an acceleration of 1 meter per second, chuck all of that in, there we go, you can see we've got c equals 1. And if c equals 1, that means that thing there still exists, but 1 times mass times acceleration, we don't need to use it. So what that does, it essentially gives us that, which is Newton's second law. Force equals mass times acceleration. And like I said, that is going to be underpinning virtually everything we do from here on in. Genius. So let's have a look at what that means in terms of this old chest. What is the difference between weight and mass? The thing that confuses the living bejesus out of people right up until GCSE and probably even beyond. Here we go. So the mass of an object is the amount of matter it contains, the amount of stuff inside something, measured in kilograms. Whereas the weight of the object is a force, and it's that force due to gravity. So there's our books, and if we consider what's happening, we've got it's falling due to gravity, so it's the force, or its weight, is what's causing it to accelerate as it falls to Earth, and its the acceleration is due to gravity, so that's measured at that acceleration is 9.8 meters per second. That's a constant value. So if we use force equals mass times acceleration, then weight is mass times gravity. And so therefore, if a book had a mass of 1.25 kilograms, notice measured in kilograms, its weight would be 1.25 times by g. Bearing in mind that is absolutely not grams, that's g, that's acceleration due to gravity, which turns out to be 12.25 newtons. Notice again, mass measured in kilograms, force measured in newtons. So the weight is a force, the mass is the amount of stuff it contains. And this idea of weight being mass times gravity is something we're going to see over and over and over again. Just as a little note there, I know physicists, you might be working with these kind of things in your physics lessons, and I believe on the physics courses they use 9.81 as your fixed value for gravity. On the maths, it's 9.8, and the reason for that is it just sometimes makes our calculations a little bit easier in terms of things start to cancel out. So we're using 9.8 as a fixed value for gravity. Okay, last other little note to mention that in reality, the value of g changes as you get further from the centre of the Earth. So on the Earth's surface where we are at the moment, 9.8. If you end up on top of Everest, it's slightly less, 9.79 something. And on the Moon, for example, g would have a value of 1.6. The important point to note there is on the Moon, this last bit here, if g was 1.6, our book would still have the same mass, but its weight would be totally different. Okay, so here we go. Let's put all of that into an example and start calculating forces that are acting on objects that are moving. So what we've got is a crane lifting a concrete block, and it's accelerating upwards at 3 meters per second squared. We've got a force in the cable, which is going to be calling tension, and we want to know what is the mass of the block. Right, it's mechanics. I can't emphasize this point enough. This big flashy swirly thing that's coming up here. Always, always, always start by drawing a diagram. If you don't draw your diagrams, guaranteed you're going to get something wrong somewhere. You might look at these from the start and think, well, why do I need to bother? It's all a bit simple, but get into good habits and get into habits earlier. Okay, so there's my block, and there's the tension in the cable. That's a force that is causing the block to move upwards, and the only other force acting on that object is gravity, which is mass times the acceleration, which is gravity, mass times g. So we've got that, and we know also that it's moving upwards. It's accelerating at 3 meters per second squared, and now what we're going to do is take all those pieces of information and put them into force equals mass times acceleration. So force is on the left, mass times acceleration on the right. Okay, so what I'm going to do is resolve my forces in the vertical direction. This is my shorthand for percent. That's what I'm going to do. Later on, you'll see you get situations where you've got horizontal forces as well, and you have to kind of split those two things out. So this is just my shorthand percent. I'm resolving going upwards, and so let's say forces on the left, acceleration, mass times acceleration on the right. So I've got my two forces, and here we've got the acceleration, which is 3 times by the mass, so that's m times a. Okay, so what I've got now is to work out what m is, so it's my only variable in there. Don't get caught out by the fact you've got this g, don't get that thing is a constant. If you prefer to just write that in as 9.8 now, that's entirely up to you. I prefer to leave it as g for as long as I possibly can, because as you'll see, particularly next year when life gets more complicated, it's easy to leave it as g, because then things can start cancelling and factorising, all the rest of it. So I've done a little bit of rearranging, factorise on the right, and then do some dividing, and we end up with our value for m, which is 500 kilograms. Okay, another example. So here we go again. Let's draw a forces diagram. We've got a wagon of mass 250 kilograms being pulled along a level track against a force of 150 newtons. The wagon starts from rest, and after 10 seconds it's covered a distance of 60 meters. That bit we will come to in a second. So first of all, find the tension in the cable. So first job is always draw the forces in. So here we go. So there's my resistive force, 150 newtons. I've got a force that's pulling it that way, so that's going to be, I'm going to call that tension again. And just for the sake of completeness, I've got reaction force and I've got weight. Now, these forces here, I'm not really going to need, because we're just going to be looking at what's going on horizontally, but it's always, again, a good habit just to put all the forces in. So, what we're going to do is go for force equals mass times acceleration, with that being my positive direction. So we're going to go in the horizontal direction this time, so that's what that in shorthand there is saying. So forces on the left, t minus 150, equals mass times acceleration, 250a on the right. Now, if we want to work out tension, you can see straight away we've got a problem, because we've got two things we don't know in this particular case. We don't know the tension, we don't know acceleration, so we're going to need to pull some extra information from somewhere, and that's where these extra bits come from. As soon as I see information about kind of displacement, time, so all those kind of things within the forces question, straight away I'm starting to think SUVAT. So, if we have a look at SUVAT, and let's say we'll go from SUVAT, the A, there it is appearing over here. Acceleration is the things that links your forces, mass times acceleration, with your SUVAT equations. It's the one thing that's in both. So we're going to link these two things together. So I'm going to find acceleration from over here and use that to then find my tension over here. So SUVAT, that's S, that's going to be 60. U says starts from rest, so that's 0. V, I don't know, don't need, don't care. A is the thing I'm trying to find. T, 10 seconds. So what are we going to do? We're going to use the one that doesn't involve V. So that would be S equals UT plus half AT squared. Plug in the values. There we go. And we end up with a value of A that's 1.2. And that's done my job over here that I needed. So now I can take my value of acceleration from my SUVAT and stick it in to this equation here. So there we go. And that allows me to work out the tension. Right, carrying straight on, here we go with another example. And let's say there's, I think there's this one and one more to go. If you're kind of happy with what you're doing, you might want to crack on and do some practice now. But if you want to look at another couple of examples, then please feel free to continue onwards. Here we go. So here's my caravan, 350 grams, towed along a straight road. We've got tension. That's the force that's causing it to be towed. We've got a resistive force of 450. And then we've got our vertical forces as well. And so we've got acceleration in that direction there. It says the driver sees a red light in the distance, so slows, taking 40 metres to come to a complete stop. Find the force in the tow bar connecting the car to the caravan. Right, so let's start off with our force equals mass times acceleration. And there it is, similar to before. And again, we've got exactly the same problem, and we probably recognise from the question that we've got all this information here, 40 metres to come to a complete stop, starting at 60 metres per second. Let's go SUVAT and plug those values in. So it takes 40 metres, starts at 60 metres per second, comes to a complete stop. A is the thing we want to find, T is the one we haven't got. So that's going to be V squared equals U squared plus 2AS. Work it through, and we can see that our acceleration is negative since we are decelerating. Right, now, the reason I've chosen this example is because I've got this force here, which is originally the force that's pulling the caravan along. But if you think about what's happening when that car brakes, it's the car that's braking, not the caravan. The car starts to brake, the caravan now wants to move faster than the car, but it can't move past the car because obviously it's being towed. And so it's the car that's actually slowing it down. So what we find is this force that was a pulling force that we call tension is now actually acting in the opposite direction. It's causing it to slow down. Now, what we'll see, we'll continue to model it like this for now, and we'll see what happens to our value of t, and it might be able to guess what's going to happen a little bit. So let's put our value of a into there, and you end up with the value of t, and that value of t is negative. And what that's telling me that t, instead of pulling it forwards, is actually another force that's resisting the motion, slowing it down, so it's actually going in this direction. It's going in the opposite direction, which is why it's negative. Okay, so that's what I'm saying, that force there. When it's a pulling force, we call it tension. When it's a pushing force going in the opposite direction to motion, we refer to it as thrust. But it, we're still going to call it T. You can recognise whether it's thrust or tension depending on the sign relative to which direction you're modelling it. Okay, so tension acts away from the object, and thrust is acting essentially kind of towards the object. On we go, last example, and this is exactly the same thing, but just done using vectors. So we can still use our force equals mass times acceleration using vectors, because acceleration is also a vector quantity. So here's our object of mass 2 kilograms. We've got our one force going that way. We've got our other force going that way. We're told F2. That's the thing we need to find. So I'm just going to describe it in terms of a vector using P and Q, just two values. And we've got acceleration, which is going off in that direction. So F equals ma. So we've got that. So force is on the left. Mass times acceleration on the right. And mass is just a scalar quantity, so we can just multiply that vector there. So we've got that going on. So we can see straight away that 1 plus P equals 2, so that gives us P is 1 and Q is minus 20, just by looking at the bits on the top and the bits on the bottom. We're being asked for the magnitude and direction of the force, so there we go. So if we've got a force F2 that's 1 minus 20, that's going down like that. And we're going to define that value there as being theta. So magnitude, first of all, is the bit of Pythagoras. There it is. As it turns out, it's just above 20 newtons, but if I round that to three significant figures, that's 20.0. If you put that into a calculator, you'll see it's slightly bigger than 20 newtons. And then the direction, tan to the minus 1 of, there you go, opposite 1 over 20, which is 2.86 degrees. Here we've got to be a little bit careful, because we've got to say, well, if that's 2.86 degrees compared to what? So I need to say very clearly it's an angle of 2.86 degrees compared to the downwards vertical direction. So we're defining that direction in terms of either I, or in this case negative g, but I'm making it clear in my statement what I'm comparing the angle to.